Okay, good morning, Professor David J. De Los Reyes. It's October 14, 2023, and the time is 6:41 a.m. Okay, my topic for this session will be a continuation of AC machines. Okay, and this will now be lesson number 39. We are running smooth. Okay, this is still a topic on transformer. Okay, let's proceed. The subject matter for this morning will be, this is a continuation of AC machines. This will be AC machines, lesson number 39. And the title of the topic will be, it's a very interesting one. We are doing this in the actual world, okay? Transformer delta connection, voltage and current relations. If the connection of a transformer is delta, what will be the relationship of the voltages and currents? The last discussion, the last time around, I think I've given you the concept on the so-called Y connection, the relationship of the, if the connection of the transformer is Y, I derive to you guys the relationship of the voltages and current. For a Y connection, the phase current is equal to the line current, but with respect to the voltages, the line to line voltages is actually greater than the phase voltages. For a Y connection, the line voltage is square root of 3 times the phase voltage. The line voltage is actually square root of 3 times the phase voltage. That's for a Y connection. For this morning, we will be deriving the relationship of the current and voltages. I think I will give you the result now before I will proceed with the derivation. In general, for a delta connection, the line current is square root of 3 times the phase current. It is the reverse, okay? Because for the Y, what is with the factor square root of 3 is actually the voltage. But for a Y connection, the line current is greater than the phase current, and the multiplier is also square root of 3. And the proof that the factor is square root of 3 are all this, we discuss next one. And the other relationship is that the line to line voltage is equal to the phase voltage, meaning the voltage across any two lines, okay, is equal to the phase voltages, equal. Okay, but for the current, this current is bigger than this current by a factor of square root of 3. Okay, let's try to bring out the figure for this one. Before we could derive the relationship of the voltages and current, we must have to draw the circuit diagram. We'll just take the secondary side of the transformer. Secondary side. So if the connection is delta, we got it is what we call this a triangle, right? We got three intersection points. And connected between these intersection points are the so-called phase windings. Phase winding number 1, phase winding number 2, phase winding number 3. And if we connect a line to these terminal points here, okay, we call these lines, output lines, right? Output line, output line, output line. So what we will be deriving will be the relationship of this line-to-line voltage with respect to the phase voltage, and the line current, the current going to the lines for the output lines with respect to the current per phase. The current circulating on the windings are all similar, but their angle with respect to each other are actually different because they don't occur at the same time, okay, as the voltage is induced on the secondary. They don't occur at the same time. The first one will occur ahead, the next one will lag behind by 120 degrees, and the third one will lag behind by 240 degrees. That's why it is three phase, right? Okay, let's try to bring out the designation for the voltages. If we call this terminal A, terminal B, and terminal C, the voltage across AB will be BAB, the voltage across BC will be BBC. This is subscript, right? And the voltage across terminal C and A will be B sub CA, and we call this phase voltages. The voltages across the windings. We call it phase voltages. Okay? For the designation of the line voltages, there are also three line voltages. If we take our voltmeter, we place it across this. That will be across terminal A and B. We call that line-to-line voltage. And if we got our voltmeter, we put it across what we call this B and C. Okay, we put it here. So this will still be line-to-line, B and C. Okay, this is terminal B, this terminal B. We still call this line-to-line voltage. And the third one will be the voltage across A and C. That is still a line voltage. So we got three line voltages here, right? It's three phase. Okay, and the voltage BAB, BBC, and BEC are all phase voltages. It's three also. So that's why a three phase voltage. Okay. Okay, let's now try to designate the currents. Since we are given 3 points on the delta connection, it's better to designate the current coming from one point to another. So we call the current coming from A to B to be IAB. The current coming from B to C will be IBC. And the current coming from C to A will be I sub CA. And we call these three the phase currents. Okay, phase currents. Okay, let's try to bring out two formulas needed in here. Okay, this is just an addition. Okay, plus the derivation of the relationship of the voltage and current. The other formulas needed here is actually the apparent power per phase will be the apparent power total over 3, and this is the apparent power per phase. Meaning, if you try to take the apparent power that would be carried by each winding, it is this formula here. And if you want to compute for the magnitude of the current passing through its phase, the magnitude will be the same. As long as the load is balanced, the current per phase will be the same. And the computation and how to compute for the current, it will be current per phase will be the apparent power per phase over the voltage per phase. Okay? We could compute for this because we are given BE total. BE total is actually the KVA of the transformer times 1000. Okay? So if you want to get the apparent power carried by each winding, it should be the KVA times 1000 or just simply BE total over 3. Okay? And for the current, the magnitude of the current per phase, this is just an additional, guys. It will be the apparent power per phase divided by the voltage per phase. Voltage per phase is the voltage across AB, across BC, and across CA. These are the phase voltages. The line voltages are these. But luckily under delta connection, okay, the line-to-line voltages are actually equal to the phase voltages. For a delta connection. The only problem now is the relationship of the line current with respect to the phase current. That will be the one we will be deriving here. So to derive the relationship of the phase current with respect to the line current, we needed the vector diagram. Okay. This will be IAB, located at angle 0 degree. I sub CE is actually located at 120 degrees. This is 120 degrees. 120 degrees. And the third one will be, okay, 240 degrees. Or if you try to measure it clockwise, it should be negative 120 degrees. Right? They are balanced. Okay, that's why I told you the current IAB is not in phase with ICE, is not in phase with I sub BC. This will occur first, this one will be next, and this one will be next. And you could actually visualize this on the graph. Right? That's the first one, the second one will be this, the third one will be this one. So this is the first one, second one, third one, it is three phase. They don't occur at the same time, okay? Hola, let's now try to consider the junction B. Where's junction B? It's this. To derive the relationship of the currents, line currents with respect to the phase current, we consider junction B. Anyway, the circuit is balanced, so we don't need to take the consider point A and point C. We just consider point B, because whatever relationship that will occur here, it will be the same as with regards to point A and also with point C. So considering junction B, sigma notation, capital letter I, and D should be equal to 0. So the meaning of this, the summation of the current, considering junction B and D should be equal to 0, the designation is this one. Current entering is plus, current leaving is minus. Current entering junction B is actually IAB, right? It is plus. And the current leaving junction B is IL1, so it's minus IL1. And the other current leaving junction B is I sub BC. This is minus I subscript BC, and this should be equal to 0. Current entering, this is leaving, okay, and this should be equal to 0. Manipulating this equation, we will compute for IL1. IL1 will be, we put this on the right, then we try to rearrange. Capital letter I with the subscript L1, meaning line current number 1 should be equal to the phase current IAB minus IBC. To subtract this one, we must have to express this one in the so-called rectangular form. Because currents in alternating current circuit and also with transformers are actually complex numbers. So if we try to subtract this one, we don't subtract it algebraically. We subtract it by using complex numbers. So to subtract this one the correct way, we must have to express IAB and IBC in the so-called polar form. Okay, IAB is actually at 0 degrees, and IBC is actually at negative 120 degrees, right? And I sub CA is actually at 120 degrees. What's the current per phase? The value of IAB, IBC, and I sub CA, the magnitude are all the same. We call it current per phase, current per phase, current per phase. But the proper designation will be current per phase angle 0 degree, that's IAB. IBC will be the current per phase angle negative 120 degrees. They don't occur at the same time, okay? They don't come out, okay? I sub CE will be current per phase angle 120 degrees. That is in polar form. Okay? What's next? To compute for the line current, okay, by using this equation here, it is IAB minus IBC, but this is plus IBC. So if we try to take the reverse of this is plus IBC. So if we try to take the reverse of this, okay, we project this to the other side in a straight line, this will now be negative IBC, right? So the vectorial sum of IAB minus IBC is actually current IL1, right? So actually this IBC here got a vertical component, it will be this, it is this portion here. And the horizontal component will be this one, right? It is this. And for IAB is just a pure real number because it occurs at 0 degrees. So this is IAB. Real part, this is imaginary part. Okay? And the vectorial sum of this side here plus this side is actually the total current IL sub 1. So by using Pythagoras principle, the square of this plus the vectorial sum of this quantity square plus the square of this, okay, should be equal. So if we try to compute for IL1 now will be, there's a square root of this one, right? Because we are solving for IL1. And the first part will be, IAB is actually the current per phase plus IBC cosine of current per phase. IBC is actually, I per phase are 120 degrees, right? Oh. Cosine of 60. It is now 60 because we take the reverse. This is now 60. This is negative 120. If we try to put it in the other side, the resulting angle of minus IBC with respect to the horizontal is 60. Because if this is 120, this angle here is 60. Right? Okay? So if this is 60, this should be 60. Okay? The real part here is actually current per phase cosine of 60 quantity square. We take this up. Plus the imaginary part side is actually, we are just using the absolute value. It should be current per phase sine of 60. Okay? Cosine of 60 is actually 0.5 plus 1, that will be 1.5. Common factor current per phase inside, quantity square. Sine of 60 is 0.866. Okay? We take the product of this, all quantity square. 1.5 square is around 2.25. If we take this 1.5, we square it, it's 2.25. 0.866 square, that will be 0.75. So if we try to take the sum, this will be 3. The sum of 1.5 square plus 0.866 square is actually 3. But there is a current per phase, common factor, quantity square. Okay? 3 is not a perfect square. This is loss of exponent. Product, right? So we could take the, what you call this, square root separately. So square root of 3 times current per phase square will be square root of 3 times the square root of per phase current square. It's a perfect square. It will just be simply current per phase. So in general now, okay, we derive it. The line current, the line current for a delta connection will be square root of 3 times the current per phase. Okay? And for the voltage, it is just by inspection. The voltage across this, which is the phase voltage, will be equal to the voltage across this, which is equal to the line-to-line voltage. Okay? They are equal assuming the resistance of the connecting wire will be negligible. Meaning, the impedance of the line, Z line, is approximately 0. But if they are not equal, there's a little bit difference, but for the meantime, for simplicity, we assume that the impedance of the line separating this point here and this point will be 0. So whatever voltage across this will be the same as the voltage across this. And the voltage across this is termed to as the line voltage, and the voltage across this is termed to as the phase voltage. So in general, for a delta connection, the line-to-line voltage is actually equal to the phase voltage. But the other difference is the current. They are not equal. The line current should be square root of 3 times the phase current. Okay, that's it, guys. That's the relationship of the voltages and current for a delta connection. For current, line current is square root of 3 times the phase current. The phase voltage is actually equal to the line voltage for a delta connected transformer. Okay, good morning from Los Angeles. Professor David.